All right, thank you, Mathieu. Good afternoon, everybody. I hope you can hear me. All right, so today I'm going to talk to you about a new data set that I've been working on with a number of people that are listed at the bottom of this slide, namely Adam Sikulski from Lancaster University, Rick Lumpkin from NOAA UML, Lucas Antonioni from Scripps, and Maria Paisos, who used to be at NOAA UML but just took a well-deserved retirement. So I'm at the University of Miami. I'm at the Rosenstiel School of Marine Atmospheric Science, and this is work that is supported by the Cooperative Institute for Marine and Atmospheric Studies at the University of Miami, which is a cooperative institute between NOAA and the University of Miami. Okay, so this is a seminar for AOML, but since we have a wider audience of people joining us, I think it is necessary for me to give a little introduction about the Global Drifter Program. So the Global Drifter Program is funded by the US National Oceanic and Atmospheric Administration, and it maintains, with international partners, a global array of satellite track drifters. And so the need of this array is to basically acquire observations of near surface currents, sea surface temperature, or SST, as well as sea level pressure. So on the left, you see a map showing you the status of the array from last week on Valentine's Day. You saw that at that time, about 1,500 drifters were present in the ocean. All the drifters, you see a diagram on the right of the drifters. It basically is constituted of a drogue that is centered at 15-meter depth. And the displacement of the drogue is communicated by a wire to a surface buoy that transmits its position as a function of time to a system of localization by satellite. And from the displacement of the buoy, you deduce the strength and direction of ocean currents. But all the drifters are actually equipped with a number of sensors, including a sensor of temperature, which is located in the surface buoy. And so it turns out that all the drifters of the Drifter program have been equipped since the beginning of the array in 1979 with a temperature sensor. So before I continue, I just wanted to get a question out of the way that is a valid question to ask is a Global Drifter program drifter actually measuring the quantity that is called SST? So on the right, you see a diagram of the drifters that are built by Scripps Institution of Oceanography, and you see the diagram of the surface buoy, and you see that the surface temperature sensor is located on the lower part of the buoy, and it's actually at a depth of about 18 centimeters. So on the left, you see a diagram of various definitions of the quantity called SST, put together by the Group for High Resolution SST or GREST. And you can see that depending on the time of the day, or depending on the depth at which you're acquiring observation of seawater temperature, you have different definition of SST. As an example, if you are at nighttime or in strong wind conditions, a profile of temperature as a function of depth would look like the red vertical line on the left. On the other hand, if you are in daytime condition or in light winds condition, the profile of temperature as a function of depth will look like the black curve on the left here. So in conclusion, I have talked with a couple of people, and really you can say that the temperature measured by a drifter is really the seawater temperature at depth of 18 centimeters. But for the rest of this talk, and for brevity, I will just use the term SST. So the Global Drifter program transmits its SST data to operational users via the World Meteorological Organization Global Telecommunication System, or GTS. So that's one thing. And then later on, the data are also distributed to research users in the form of quality control delayed mode products. And so the release of quality control data products is led by the Data Assembly Center, or DAC, of the GDP, which is located at AOML in Miami, Florida. So the drifter data, including SST, are harvested by a number of national and international projects and organizations. And these projects aim at assembling in situ SST observations to produce quality control and reformatted data sets for calibration and validation of satellite-based SST observations, for scientific analysis, or for climate monitoring. One such example is IQUAM, which aims at producing a quality control dataset of in situ SST, including from drifters, but also from ships and from moored buoys, monitor the quality control of in situ SST on lines, and then serve reformatted in situ SST data with quality level and flags appended to this data. Another example is ICOAT, the International Comprehensive Ocean Atmospheric Dataset. So if you consider these datasets, they are going to contain the SST data from the drifters. And I guess I wanted to use a quote from a paper by Lucas and Trevoni et al. In 2019 as part of the OceanObs 19 collection, where he states that today, SVP drifters provide more SST observations than any other source of in situ data, including ships by a factor of 4, coastal moorings by a factor of 4, tropical moorings by a factor of 50, or Argo floats by a factor of 100. And then another example of the importance of drifter SST data is the diagram that is shown on the right. As you may know, the United Kingdom Met Office Hadley Center put together the HAT SST4 dataset, which is a monthly global field of SST on a 5 by 5 degree longitude grid from 1850 to date. And this dataset is very important because it's used not only to monitor climate and to look at climate variation in the past. And on the right, you can see a diagram that shows you the fractional contribution of different SST observation platforms. And you can see on the right how the portion from drifters globally is basically reaching today about 50% of the data that are going into this dataset. So the drifter data, the SST drifter data, are very important data for climate monitoring, among other things. So the Global Drifter Program, as I said, also produced some quality controlled products at a later time in daylight time that you may have used yourself for your oceanographic research, especially if you're looking at velocity. So here I'm showing you a table that tells you what is currently available. So there is a data set of estimated position and velocity from drifters at 6 hourly intervals along drifter trajectories. So the methodology to derive this data set was described in a paper from 1996 by Hansen and Puma. And this paper also described how a 6 hourly product of SST is also derived using the data of the Global Drifter Program. More recently, since 2016, we've been releasing an hourly data set of position and velocity that was described in a paper, Elipot et al. From 2016. And the goal of the paper that we recently submitted, and that I'm presenting you today, hopefully it will be Elipot et al. 2022, is describing the methods that we've put in place in order to derive an hourly data set of SST estimates along drifter trajectories. And so this manuscript was submitted to a journal called Scientific Data, and in the form of a data descriptor paper. That is, it's a new type of publication that provides detailed description of research data set, including the methods used to collect the data and technical analysis supporting the quality of the measurements. So I will be dwelling into the details of deriving the hourly drifter data set today. And I will not be talking too much about application from this data set, but I'll show you some preliminary results on future work just to whet your appetite in a little bit. So the goal really of this new data set is not to supplement or replace the existing quality control data set for climate monitoring, but it's rather to add SST to the data set of hourly position and velocity to investigate small scales and large scale processes in the ocean. So the currently available data set of position and velocity is in its version 1.04. It totals 17,324 trajectories, comprising approximately 166 million estimates of position and velocity from 1987 to 2020. And so by adding the data set of SST, as I will describe to you, this data set will reach its version number 2 with a number of added SST variables that will be released upon publication of our manuscript. So now I'm going to talk to you about how we derive this data set, and really we have an estimation problem. And I wanted to illustrate the problem or the topic at hand by giving you one example of probably maybe a typical time series of SST observations from a drifter, ID number 55366. That's a drifter that was tracked by the system Argos of the type SVP, meaning it was recording temperature, and it was built by the company named Pacific Gyre. So you see the time series of SST acquired from this drifter, and you see the trajectory of that drifter in the North Equatorial Pacific. Atlantic. Over the length of his drifter trajectory, 408 days, it acquired 10,605 SST observations. And one of the things you can see right out, I hope you can see on this graph, is that you actually have some outliers, SST observations that obviously are, departing greatly from what you would expect, or the average SST along this trajectory. So first of all, first point, we have outliers. We have bad data in the data set. The second thing that I would like you to realize is, as an example, you can plot a time series of temporal intervals between consecutive observation of SST on the drifter. So as an example, this drifter was sampling SST every 60 seconds. Every 15 minutes, it was averaging those 16 samples, and it was transmitting its data every 90 seconds. But because it was an Argos tracked drifters, it was basically transmitting continuously until a satellite was flying overhead of the drifter, and where the drifter was able to transmit its data. So it results into a very uneven sample type of time series when it comes to SST, and it looks like what you have on the graph showing here on the left. And so the Argos satellite orbital period is about 101 minutes, and it explains why you have partly some of these patterns. So we have uneven sampling. The other thing that we have is that for about 85% of the drifters, observations are derived from what we call an SST equation, where basically the SST returned by a sensor is equal to a factor A times N plus B, where A is effectively the resolution of your sensor, N is a binary bit count, and B is just an offset. So here for this drifter, the binary bit count was coded over 10 bits. And so with the coefficient A and B, you can actually deduce what are the range of observable values. So if you plug in the numbers, you're going to find out that this drifter is going to be able to return values between -5, shown here, and 46.15 degrees Celsius, shown here. So this is the second thing this is one of the things you want to consider. And then this factor A is effectively giving you the resolution of the data. So here I'm zooming on this time series, and you can clearly see instances of consecutive records during which the temperature returned by the sensor was actually not changing. So you have a quantization of the values. You have quantized values. It doesn't mean that the temperature measured in the ocean was not changing. Rather, it meant that it was changing by an amount that the SST sensor was actually not able to capture. So we have one solution, which is the 6-hourly product, which is currently available. So we can estimate we have already an estimate at 6-hour intervals along a drifter trajectory of SST based on this data. Here I'm showing you an example for the same drifter. So kriging is kind of like an optimal interpolation method, and it uses phase observation before and after the estimation times, and it needs some assumption about the covariance structure of your data. So there's a number of reasons why we are not going to use these methods to derive the new product, and I'll be happy to talk to you about it at another time. But it's not my favorite method. So the new estimation, how are we going to deal with this? So I wanted to show you again how heterogeneous the data set is at the base. So I was telling you about the resolution of the data. So on the left, you're going to see here on this panel B, a histogram of all the resolutions that we've been able to find in the data set. So we've identified, as an example, 179 different types of resolution in the SST observations. And you can see how those resolutions change as a function of time. On the right, you see also a distribution of the time intervals between SST observations for drifters that were tracked by the system Argos, you can see here on the bottom, or for drifters that were tracked by GPS but had their data transmitted by the Iridium system, which is the latest generation of drifters, as you can see here. So nevertheless, if the drifters were tracked by Argos or by GPS plus Iridium, you can see that even from Argos, early on in the early 2000s, you already had a peak in the distribution that was centered around 1 hour. So you already had relatively high resolution SST observation from the drifters. Would they be from Argos or would they be GPS tracked? So the goal here is going to be to find methods to automate the process and to estimate SST at, let's say, a time t equals tk. So the way we think about it, we're going to consider the following process model, where around the time tk, the observations at times ti are basically the sum of a process, a SST model, plus some noise. So the noise component, var epsilon, is expected to have zero mean, to have unit variance, but it's locally scaled by sigma, which is the error variance of the observations. So basically, we're going to try to find a model that is going to be able to capture variability of SST as the way SST is changing in the ocean, and everything else that we're not going to be able to resolve is going to be lumped into the noise, which could be geophysical noise, that is variability of SST, which is not captured by the record, or instrumental noise or transmission noise. So we have this process model, as I told you, but what about this model of SST temporal evolution? So we're going to use a model that has two components. The first component is called SP, and the second component is called SD in this case. And the two components of this model model two very different things. The first part, SP, is going to model a low frequency temporal evolution of SST. And we don't know a priori what should be the shape of that function, so we're going to assume that we're going to be able to approximate with a polynomial of order P, capital P. And you can think of a polynomial as being an approximation of an unknown underlying function, just like you would do a Taylor extension of a function you don't know. And for the other component, which is basically a diurnal component, because we think that this diurnal component, or we know from previous studies that this diurnal component is going to be periodic, it is natural to try to decompose it like we would do with a Fourier series, and we're going to write it as a sum of n cosine function with an amplitude a and a phase phi. We can rewrite this cosine function as being the sum of a cosine function and a sine function with two different amplitudes and no phase. So if you look at this model in the end, you see that in order to get an estimate of the SST, we need to estimate p plus 1 plus 2n parameters at every time step tk. Now, if we actually want to get the estimate, we need to evaluate this function at times t equals tk. And the estimate of SST itself is only the sum of n plus 1 term. We have the first term, which is the order 0 of the polynomial. And then we have n terms, which are basically the amplitude terms that are in front of the cosine function. How does that work in practice? Here I'm showing you an example. So we have our process model. And here we have a zoom on a time series of about 1 to 3 days of SST observations. And we want to know what the SST, we want to get an estimate of what the SST is exactly at this time tk. So what we can do is that we're going to consider all the observations around this time tk. And so we're going to define a parameter called the bandwidth, h, and we're going to consider the observation within plus or minus h from that time tk. And then we're going to, apply the evolution model. And let's say we're going to say, you know what, we're going to think that this evolution model is going to be a polynomial of order 1, and it's not going to have a diurnal evolution component. So it's going to have a parameter n equals 0, and the polynomial of order 1 means you have two terms, the 0 term and the 1 term. So what that means is that you're basically modeling the evolution of SST within that window as a straight line as a function of time. And the value at tk is basically this expression evaluated at time ti equals tk, and it's going to be basically that red dot in the middle. That's the value s naught that you're getting here. So you can see that this model is capturing maybe the low frequency rise of temperature within that bandwidth. But it's clearly not capturing those oscillations that happen every day that we know are related to diurnal oscillations. So we can go one step further, and we're going to say, you know what? We're going to use a polynomial of order 1, and we're going to use 3 harmonics of the diurnal frequency. We're going to use 3 cosine function. Once we do that, then we obtain an estimate, which is in blue for the curve within this bandwidth. And the estimate at time tk is actually this expression evaluated at times ti equals tk, which is a blue dot now here. And the interesting part is that you can actually decide to evaluate the component that is due to the low frequency part. That would be the red dot. And you can only decide to evaluate the component that is due to the diurnal part, which is 0 mean and would be an anomaly around 0. And when you sum the two, you get the blue dot. So then you can just slide your window and get an estimate at another time. And then you can slide your window again and get again an estimate at another time. So this is the principle of the methods. We're going to fit a model to the observations in a sliding window at every single observation time. So I told you we were going to estimate the parameters. So the methods to estimate the parameters is actually a little complicated, but I'm going to try to summarize it here in the slide. And if you want to know all the gory details, please refer to the paper. We have a preprint about it. But what we're going to do, we're going to apply a weighted least square estimator at all the original observation times using a sliding window with a bandwidth of 1 day. Then we're going to analyze the residuals from the fits, and we're going to downweight the observations based on the size of these residuals. And then we're going to repeat 3 times, step 1 and 2, and each time we're going to iterate the weights assigned to the data in order to downweight and what we call robustify, if that's a word, the weight that is actually given to the data. And we're going to do that at a number of 4 times. So we're going to have 4 estimations. So these are estimations that is done at the original observation times. And then once we have our robust weights and we're happy with these weights, we're going to apply a final least square estimator with the penultimate robust weights. But this time we're going to do it at regular hour times, midnight, 1 o'clock, 2 o'clock, etc. So we're going to have a regularly estimated SST along the drifter trajectories. And then as a final step, we're going to estimate the error variance from our process model. And we're going to estimate this error variance from the residuals of the fit. And we're going to propagate this error variance into the estimation of the parameter uncertainty and the SST uncertainty. So the methods is adapted from a method called the LOAS that you may have heard of, and which stands for the locally weighted scatterplot smoothing estimator, which is due by Cleveland from 1979. However, one thing that I didn't talk about is how we're going to choose actually the model to apply to our data. As I said, we're going to have a polynomial of order P, and we're going to have a given number of harmonics of the diurnal frequency. So we tried a number of models, and we tried 14 different models, but we tested on a subset of the global drifter data set. So we randomly selected but globally distributed 19 different drifters, and we tried those 14 different models. So we tried that on only a few selected drifters because it's actually very computationally expensive to try all these models on the global data set. And what we did is that we considered 2 different metrics to try to see which model was the best. And so we considered the root mean square error, which is basically the square root of the average of the difference between the estimates and the data. And then we considered another metric, which is the error variance estimates. So ideally, you would want the error variance to be minimal, and you would want the RMS error to be also minimal. And what we found, despite these 2 metrics not being independent, is that depending if we were changing the order of the polynomial or changing the number of harmonics used, those 2 metrics were changing differently. As an example, if we had a fixed number, if we had a polynomial of order 0, but increasing the harmonics from 2 to 3 to 4, we would be able to reduce the RMS error vertically, but we wouldn't change the error variance. In contrast, if we used a fixed number of diurnal harmonics, but we increase the polynomial order from model 1 to 4 to 7 to 10, then we would reduce the error variance estimate, but we would not reduce the RMS error. So what we found, testing those different models on the 98 drifters that I told you about, and so we found some differences in the results, which is indicated by, we found some scatter in the results, which is indicated by the ellipses. But we settled on model number 5 because increasing the number of harmonics or increasing the order of the polynomial was not significantly improving the performances of the model. So settling on model number 5, which is the one that has a polynomial of order 1 and 3 harmonics of the diurnal frequency. So we need to estimate 8 parameters at every time step. So how does this model work in practice? So I'm going back to this example that I showed you earlier. So one of the good things about this practice is that this method is that it's actually iterative. And so as you downweight the observations, some observations end up having a weight of 0. And these are the observations that are actually circled with the black circles here. So this method is actually able to identify and eliminate, in some sense, the outliers in the data. So that's a good property of this method. So the second thing is that when we run the estimation at the observation time. So here's an example, again, a little zoom, an example of the outliers. So now we get an estimate of the low frequency components, which are the red dots. And we get an estimate of the low frequency component plus the diurnal component, the sum of which are the blue dots here. And you can compare the blue dots to the black dots that correspond to the observational data. So here I'm trying to make a distinction between observations in black and estimates, which are the colored dots. And as I said earlier, we can estimate uncertainty in the parameters for both the low frequency component and the diurnal component, which are indicated by those vertical lines. And then the next thing that we do is that we can actually conduct the same thing, but estimate it continuously at any time. And we happen to do it at early time steps. And now you see the shading that correspond to the uncertainty and the curve that correspond to the various estimates. And one of the things that you get, and you could see in the previous slides, is that you actually get an estimate of not only the uncertainty. So as an example, here it's on the log scale for the same plot as I showed you before, starting from the bottom. You can see that the low frequency estimate, the red curve, has relatively low uncertainty. You can see that the diurnal SST uncertainty is actually much higher than the low frequency uncertainty. And it dominates actually the total SST uncertainty in the estimation. And then another thing that we actually get an estimate of that error variance, of that sigma square, the square root of which parameter that I was telling you about that is part of our process model, but it's basically telling you the amount of variability that we're actually not able to capture with our model. And that could be of use. And the residuals, the absolute value of the residuals are actually shown here with the black dots. So this method is actually able to really reduce the amount of scatter we have in the original data and provide consistent, well-behaved estimates that have quantified uncertainty. So we quantify the uncertainties, as I said, but without getting too much into the details, I wanted to tell you that we estimate a total error variance estimate that comprise two terms. The first term is actually estimated directly from the fits, from the residuals. And it has another term, which could be called the resolution of the quantization error variance, that basically take into account the resolution of the drifters. So we've been able to consider the resolution of each individual drifters and incorporate this added uncertainty into our estimate of total error variance, as well as the derived uncertainty estimates for the SST estimate themselves. So on a global scale, as an example, we find that the uncertainty, the error variance for the drogue drifters is less than it is for the undrogue drifters, informing us that if you actually take SST data from a drifter, you might want to see if it's drogue or if it's undrogue, meaning it has loss in stroke, because the error variance is going to be different. As an example, we estimate that a global value for the error variance, the square root of it would be 0.031 for drogue drifters, but it would be 0.036 for undrogue drifters. But those global values at the peak of the distribution of the global values actually hide the fact that you have some large spatial variability in this error variance estimates. As an example, you can see that in regions of high eddy kinetic energy regions, such as the western boundary currents, the ACC, or even under the storm tracks and the wind-driven currents, you're going to find a lot higher error variance in our estimate. We also been able to derive a quality flag to add the interpretation and the use of the data. And we've derived quality flags for the non-diurnal component, the diurnal component, and the total component. And so the scheme is, I will gloss over this, but it's basically described in the paper. And we basically consider the estimates and its uncertainty confidence interval with respect to a range of physically plausible values of SST. So a few global results on this new data set. So first of all, here on the top left, I'm showing you a mean, a gridded mean SST from this new data set. So it looks approximately what you would expect in the ocean. So we're not doing too much of a bad job. But what is interesting is that you can look at the standard deviation of SST from the drifters on a global scale, and it looks like this. And you see that, once again, you have high SST variability in western boundary current regions and the regions of strong wind forcing, as well as along the equatorial regions, etc. And what you find also, you can actually distinguish the standard deviation of SST that is due to the non-diurnal component from our fit, and the one that is due to the diurnal component from our fit. And one of the things you can see, you were hard pressed to see much of a difference on this global scale between the non-diurnal component and the total component here on the lower left compared to the top right. Meaning that the standard deviation of SST is actually on average an order of magnitude smaller for the diurnal component than it is for the non-diurnal component. However, you see again that you have some differences as a function of space. However, the spatial distribution for the non-diurnal SST standard deviation is different than it is for the diurnal SST standard deviation. About the uncertainties as well, so we estimated the uncertainties globally, and what we find is that the non-diurnal uncertainty is a lot smaller, on the order of 6×10⁻³ degrees Celsius compared to the diurnal uncertainty on our single estimates. But for the total, as an example, we find also that, once again, the uncertainty in the product are higher for undrugged drifters compared to drugged drifters. And then here, once again, you see global maps of the uncertainty in the estimates of non-diurnal SST, diurnal SST, and total SST. And you can see again that you have some large geographical differences in those estimates of uncertainty. So in final, the final data set that is going to be released hopefully very soon, the paper has been under review for about a month, is going to be a number of SST estimates that are going to match the existing version 1.04 of the drifter dataset of position and velocity. So out of the 754,333 estimates of position and velocity, we're going to be able to add SST estimates to about 95.59% of those, about 158 million of SST estimates of quality, quality level 5, the highest quality level. Here you see a histogram of the distribution of those estimates of SST as a function of time. The total is a red histogram, and the number of diurnal estimate, which is lower than the number of total estimate, is actually shown here as a function of time. And the reason why it's lower is because we have different quality flag for the diurnal component that we have for the total or for the non-diurnal components. So here I'm showing you a histogram of the highest quality estimates that we have as a function of time. And you have less quality 5 estimate for the diurnal component compared to the total component. And on the left you will see a density of observations of quality 5 SST estimates at hourly time step along drifter trajectories. So the final data set, we're going to add 9 new variables to the hourly positions. We're going to add seawater temperature, which is basically the sum of the non-diurnal and diurnal components. We're going to provide the seawater temperature estimate with 3 decimal places, with the last digit rounded towards the nearest 10⁻³ degrees Celsius. We're going to provide, for convenience, we're going to provide you also the 2 components, the non-diurnal component, SST1, that I've been referring to earlier, as well as the diurnal component, which is an anomaly, a zero mean anomaly. So in the data set, if you sum SST1 and SST2, you'll get the total SST. But for convenience, we're going to provide you with the 3 of them. We're going to provide you with an uncertainty for every single one component, for the total, the diurnal, and the non-diurnal. We're going to provide you with the standard uncertainty 1 sigma. And we're going to provide you with a quality flag for each single one of these estimates as well. And with this, I'll end up with a couple of movies that are showing you the illustration that illustrate on the right the low frequency evolution, this first part of the model that I used, and on the left is showing you on a different time scale the diurnal evolution of SST for a cluster of drifters that were released during the SPURS experiment in the North Atlantic. All right, and so with this, if you have any question, please reach out to me later on or right now. And the paper is submitted and it's actually available as a preprint if you want to know more details about the methods. All right, I think I'm done.